So let's get going. So the material on the exam will cover everything up through this lecture. The review on Friday will cover the material up through this lecture. There won't be any homework assigned on Friday, if I understand things correctly, but there's a practice exam that Peter will put up with solutions. It's up already? It's up already. If you look at the practice exam, and you should set yourself, just do a little study, sit down for an hour, time yourself, practice working through the problems, doing triage on the problems, compare with the solutions, and we'll have the hour exam in class on Monday. I realize that the first hour exam was quite long, and I'm going to try to adjust accordingly. Okay. So the last time we talked about how you made relations in a ring. A1 is equal to A2 equal AN equals 0 in a ring. Namely, you went to the ring R bar, which was R modulo the ideal generated by A1, A2. Because if you wanted an image of R in which all of these are 0, then any combination of them with multipliers from R. So this is the ideal consisting of all things of the form R1A1 plus R2A2 plus. It's a pretty complicated ideal because you generally don't know what's in it. But if you went to this ring, then you got an image of R. There's a natural homomorphism from R to this ring. And in this ring, all of these elements have become 0 because they're in the 0 coset. Okay. Now, this time, we're going to talk about adding elements to a ring, adjoining elements to a ring. Alpha to a ring R. Making a bigger ring, namely not making things where certain things go to 0, but making a larger ring than R. So that's easy to do if you have R contained in some universal ring. So for example, if you have Z contained in the ring C, I mean inside the complex numbers, and you take any complex number, you can take the ring R, this is the basic ring R, you can take the ring R prime where you adjoin to R anything, you adjoin to R alpha, and then you, of course, have to adjoin all combinations of alpha. So this would be the ring consisting of things of the form R0 plus R1 alpha plus R2 alpha squared plus Rn alpha to the n, where the Ri's are in R. In fact, this works for any time, not just Z, but you could take any subring that contains Z inside of C. You could take some element that, now if this element were already in R, then you get the ring R back again because all these combinations are in R. And if this element isn't in R, you get a slightly larger ring. And by putting alpha in, you're forced to put in all these combinations because the ring has to be closed under addition and multiplication.
When you're going up to n, does that mean that any n works?
Any n, of course, all n. So all polynomials in alpha have to be in the ring. Now those polynomials aren't all distinct. I'm not claiming that they're all distinct. We're going to analyze that. But at least, all I'm saying is if you try to create a larger ring than R by adjoining one element of the complex numbers that isn't in it, and you want it to be a ring, it's got to contain all of these elements of the complex numbers, because once it contains alpha and it's closed under multiplication, it contains alpha squared and alpha cubed and alpha to the fourth, all powers of alpha. And then once it contains those, it has to contain all products of those elements with elements in R. And then one checks that this actually forms a ring containing both R and alpha. If you multiply two things in here, it's still in here. So this is the smallest ring, subring, of the complex numbers containing both the original ring R and the new element alpha. So just as if we wanted to create a relation in a ring by saying A1 is equal to 0 and A2 is equal to 0, we had to admit that all these elements were 0 too because it was an ideal. Likewise, if we want to adjoin alpha to the ring, we have to agree to adjoin all polynomials in alpha. Otherwise, it's not closed under multiplication and addition. Yeah, Atticus.
What was special about Z here?
Z is just the basic ring. I mean, any ring, subring of the complex numbers contains the integers because it contains the element 1. Right? So any subring of the complex numbers has to contain the integers. So we just assume we have something. I had started off with adjoining things to the integers, but actually you could adjoin it to any subring of the complex numbers. So this is when you have some big ring up there and you add some extra element, you add all these polynomials. Now what this ring looks like depends completely on what alpha is. So let me give you two completely different examples. The structure of R prime depends on alpha. For example, this is stupid. If alpha is in R, then R prime is just equal to R. Namely, all these polynomials were already in R, so this gigantic thing could just be written as like R. Okay? That's the first observation. Second observation. More generally, if alpha satisfies a monic polynomial over R, for example, maybe not alpha is in R. This would be the polynomial, by the way, x minus alpha is equal to 0. See, that's a monic polynomial satisfied by alpha over R, if alpha is in R. But more generally, it could satisfy a polynomial like x squared plus 1 is equal to 0. I.e., maybe alpha is the complex number I. I might not be in your ring. For example, your ring might be the integers. But you found some element in the complex numbers that satisfies a polynomial which is monic over your ring. A monic polynomial of degree n over R. Then R prime consists of all, can be expressed a monic polynomial of least degree. So it's the smallest monic polynomial that it satisfies. Then R prime can be expressed as all the combinations R0 plus R1 alpha plus Rn minus 1 alpha to the n minus 1 with the Ri in R. And these are all distinct. So that so it looks like n copies of the, you could give it an isomorphism as just as an abelian group with n copies of R by taking an element, a polynomial, to its coefficients, R0, R1, Rn minus 1. So if the element is in R, then it satisfies a linear polynomial. That's of degree 1. That's the smallest polynomial it could possibly satisfy. So you just get one copy of R. But if it satisfied a polynomial of degree 2, then this ring would look like two copies of R with a multiplication. And the reason is that it's true that this ring consists of all polynomials, but once you get to the polynomial alpha to the n, then it can be expressed as a polynomial in the smaller powers of alpha because it satisfies a monic polynomial of degree n, which says that alpha to the n plus an minus 1, or Rn minus 1 alpha to the n minus 1 plus R1 alpha plus R0 is equal to 0. And taking all this over to the other side, it says that alpha to the n is minus Rn minus 1 alpha to the n minus 1 plus R0. And consequently, this power of alpha can already be expressed in terms of the lower powers. And likewise, alpha to the n plus 1 can be expressed in terms of alpha to the n down to alpha, and then you re-express alpha to the n in terms of the lower powers. So this and all high powers, all higher powers, can be expressed as a linear combination of the smaller powers. And in fact, these polynomials represent the different polynomials in alpha you get by adding to R. If there were some linear combination of this sort that were 0, so they're all distinct, none are 0. If there were some linear combination of these that were 0, then alpha would have satisfied a polynomial of smaller degree than n over r, right? Namely a polynomial of degree n minus 1. So if it satisfies, if the smallest polynomial it satisfies a monic polynomial of degree n, you get 2 copies of r. And we've seen examples of this. For example, the ring adjoining I to z is just z plus zi. Namely, I squared is minus 1, so it's already back in here. Okay, so that's 2 copies. And then finally what can happen, which is quite likely too, is maybe there's no polynomial that alpha satisfies with coefficients in R. Yes?
What if the polynomial is not monic?
Then it's much more complicated. Because if the polynomial isn't monic, you may not be able to write alpha to the n as a combination of elements in R. You'd only be able to write Rn alpha to the n. And then you don't know if you can divide by Rn to get alpha. So it's a more complicated structure if the polynomial it satisfies is not monic. However, if this is a field, then the smallest polynomial can be made monic by multiplying by the inverse of the first coefficient. So it's easier to analyze this when it's a field, and we're going to get into that a little later. But you're absolutely right. If it's not monic, it becomes quite nasty to sort of figure out which combinations can be expressed in terms of the previous ones. Yeah. No. Here could be a linear polynomial. If alpha's in the ring, this is a particular case of that. Okay? It's an incredibly stupid case, but it's one that you should bear in mind. Okay? And even more generally, alpha may not satisfy any polynomial with coefficients in R. So an example of that is if you took R to be the integers, or even the rational numbers, and you took alpha to be the mathematical constant pi, or alpha equal the mathematical constant e. Those are nice complex numbers. They're called transcendental numbers because they don't satisfy any polynomial. Alpha is what's called transcendental over R. And it's not easy to prove something is transcendental, namely that pi doesn't satisfy a polynomial. That's essentially the theorem that you can't square the circle. You can't construct by ruler and compass a square which has the same area as the circle. That's related to the fact that pi satisfies no algebraic polynomial, as you'll learn in Math 123. And the fact that e satisfies no polynomial with rational coefficients. Those are difficult theorems. These were proved in the 19th century. However, before they were proved, it was obvious that there were transcendental numbers. That there were transcendental numbers without knowing a single one of them. And the argument was given by Cantor, one of his great arguments using his different sizes of infinity. He said, the rational numbers are a countable infinity. You can also prove that anything that satisfies an algebraic polynomial over the rational numbers is a countable set of numbers. But the real numbers and the complex numbers are uncountable infinities. Therefore, there must be transcendental numbers. This was the first argument that really used non-equal sets of infinities. There's a book out by now by this author I absolutely hate, who's sort of a failed tennis player. What is his name? David Wallace. He writes these books. No book that he writes is less than 700-800 pages. He's supposed to be a genius. So he's written a book on Cantor's work on infinity that you can summarize in about 2 paragraphs. In fact, there's a great New Yorker review of it that summarizes the entire argument of Cantor in 2 paragraphs. Never mind. That's David Foster Wallace. You might want to read that. But the first argument that Cantor really killed by these different orders of infinity was that there were transcendental numbers. The ones satisfying polynomials were countable, The whole set of complex numbers was uncountable, therefore there had to be transcendental numbers. Then it becomes a big question as to whether you can prove a fixed constant that comes somewhere else is transcendental. An open question, which is the main open question in transcendental number theory, is whether Euler's constant is transcendental. Is gamma transcendental? So this is the limit as n goes to infinity. It's the difference between the harmonic series and the logarithm. And so it's a constant, which you can define. It's a limit. And everyone believes that this is transcendental. It's not even known that it's an irrational number. It might even satisfy a polynomial of degree 1 with coefficients over the rational numbers. That's how little we know about it. So that's much, I mean, irrational is nothing. That just says it doesn't have a polynomial like this. But I is irrational. But I satisfies an easy polynomial. Right? So gamma we don't know. So any given constant that comes up in mathematics that's complex, you can ask this question about. Now, if it doesn't satisfy a polynomial, then all of these polynomials are distinct for every value of n. Because if there were any two that were equal, that would produce their difference would produce a polynomial that it satisfied. Right? So if all those things are distinct, that says that if alpha is transcendental, that this ring is isomorphic to the ring of polynomials in X over R. There are no relations among the polynomials. So in particular, it's got an infinite number of copies of R, the coefficients of an arbitrary degree polynomial. Whereas here, we had only a finite number of copies of R because we got this thing here. And in fact, if this monic polynomial is f of x, then in fact you can show this ring R prime is nothing but the quotient of the polynomials in X by the ideal generated by the polynomial f of x. See, these are just the remainders after you do division by f of x using the Euclidean algorithm. And that works for a monic polynomial. So every coset of division by f of x would be uniquely represented by a polynomial of degree less than n. And so the ring that you got by adjoining alpha to R would be isomorphic to this quotient ring, where this is the monic polynomial of least degree it satisfies. And if it doesn't satisfy a polynomial of any degree, then you get a very much bigger ring, R of x. So adjoining an element to a ring, in many cases, produces a ring which is just a quotient of the polynomial ring by a fixed polynomial. It's more complicated if the polynomial isn't monic. Okay? So let's try a couple of these rings to get a little feel for them. But we're going to, now I should say, let's back off a little bit before we try any of these rings, that when you think of it in this way, either this or this, notice that we can now dispense with the complex numbers. We don't even have to know that alpha is up there. Namely, if we want a larger ring than R, containing a new element alpha, satisfying a monic polynomial f of x over R, we can take the ring R prime, which is you first adjoin all polynomials in X, and then you mod out by the ideal generated by this monic polynomial f of x. And the new element in this contains, this is all things of the form R0 plus R1x plus R1, Rn minus 1 x to the n minus 1. So it looks like n copies of R as an abelian group. It contains R, just mapping an element R into the constant R0. So among the polynomials of degree less than n, you have the constant polynomials. And moreover, it contains an element, alpha, satisfying a monic polynomial. Namely, it contains the element x. Satisfies f of alpha equal to 0. Because if you take the element x in this ring and you calculate the polynomial f of x of it, that's in this ideal, so it's 0 in the quotient ring. So without even having this larger ring to join elements in, if we want to add an element that satisfies a mnemonic polynomial, we just go to this ring here. And the multiplication in this ring is complicated, and it depends on what the polynomial f is. Because if you want to multiply two of these cosets, it's just like multiplication mod n. You multiply the polynomials in x, that overrides the degree. You get polynomials of degree bigger than n, and then you have to take the remainder after division by f of x to figure out what you get. So addition here is just addition of coordinates. That's easy. This tells you what the addition law is easy, but the multiplication depends on x. Because you overflow when you multiply, and then you have to gather in and take the remainder after you divide by f. So this is the adjunction of elements. And I'm going to do a few cases for you so you see how powerful this is. So in this way, we didn't need the complex numbers to make the Gaussian integers. Example, we could have written the Gaussian integers as adjoin the variable x and divide by the ideal x squared plus 1. That would produce an isomorphic ring, which wouldn't be in the complex numbers or anything. It would just be sitting there, because this has the integers in it, and then it has so this would look like z plus zx, and x squared would be minus 1. So that's isomorphic to the Gaussian integers. So let's try a few of these where we don't have subrings in the complex numbers. In fact, let's do finite fields. So let's take R to be z mod 3. Now, z mod 3, if you take the elements, there's 0, 1, and 2. And if you take the squares of elements, 0 squared is congruent to 0, 1 squared is congruent to 1, and 2 squared is congruent to 1, mod 3. So in particular, we do not have a square root of 2 in that ring. There is no element whose square is 2. So in particular, the polynomial x squared minus 2, let's call that f of x, is irreducible in the ring z mod 3z. The reason is, if it had a factor, it would have to have a linear factor. It would have to have a small factor of degree smaller than 2. If it had a linear factor, it would have a root. And there are no elements in the field of 3 elements whose square is 2. So there are no roots. There's no roots. If you have a polynomial of degree bigger than 3, you can't do this argument, because you could have a polynomial of degree 4 that had no roots but had 2 quadratic factors. But if you have a polynomial of very small degree, you can tell it's irreducible by the fact that it has no roots. Okay? So,
Irreducible has got to mean...
Not a product of 2 smaller polynomials. The same way that a number is prime if it's not a factor of 2 smaller. So irreducible, I'm sorry. This means f of x is not equal to g of x times h of x with both of degree bigger than or equal to 1. Both g and h. That's what I mean by an irreducible polynomial. It doesn't break into it doesn't factor into the product of smaller polynomials.
The polynomials would have to be in...
Oh, yes, of course. Irreducible polynomials have to have coefficients in this ring. I mean, I could always write this, as x minus the square root of 2 times x plus the square root of 2. That's a factorization of it. But this element is not in my initial ring. I don't have a square root of 2. There's no element whose square is 2. Okay? So the question of irreducibility always has to do with what ring we're working over. Okay. So we have this polynomial. So we don't have a square root of 2 in our field of 3 elements. But we might want to construct a larger ring from the field of 3 elements where we do have a square root of 2. Just like we might want to construct a larger ring than z where we have a square root of minus 1. So the adjunction construction would say, take R prime equals Z mod 3, take polynomials at x over that, and divide by the ideal x squared minus 2. That's a monic polynomial. So this is going to look like 2 copies of z squared of 3. Because any higher degree polynomial in x, I'd be able to divide it by x squared minus 2 and get a remainder, which was a linear polynomial in x. Okay? So this ring has 9 elements in it. Because I have any choice for this coefficient times any choice for that coefficient. Okay? What's the structure of this ring? What's the structure of this ring? Well, I claim that this ring is a field. Why is R prime a field? So I claim it's a field because of the following. Imagine that I have an arbitrary element in it, a plus bx, and multiply that by the element a minus bx. And that gives me the element a squared minus b squared times x squared. But x squared is 2, so minus 2b squared. And this element is in Z mod 3. And I claim it's not 0 in Z mod 3z if a and b are both not 0. Of course, if a and b are both 0, this element is 0. But if they're not both 0, then if b is equal to 0 and a is non-zero, this element is just a squared. So that's clearly non-zero because the squares of non-zero elements are non-zero. If b is not equal to 0 and this element were equal to 0, if a squared minus 2b squared equals 0 and b is not equal to 0, then a squared is equal to 2b squared. And dividing by this, I'd get a over b quantity squared is equal to 2. But that's impossible because 2 is not a square. So this element would be non-zero. And so it would be invertible in Z mod 3 because this is a field. And therefore, my arbitrary element, a plus bx, if I simply multiplied it by the element a minus bx divided by a squared minus 2b squared, which is invertible, that would be equal to 1. And that, let f be a field. Let f of x be a monic polynomial with coefficients in f. Consider the ring R, which is f of x modulo the ideal generated by f of x. Say this has degree n. No. No. Arbitrary monic polynomial. This ring, as we've seen, as an abelian group looks like n copies of f, additively. And the question is, when is it a field? When is every non-zero element in it invertible? And the proposition is, R is a field if and only if f of x is irreducible over the field f. Is that what you were after?
Well, I was also asking, in the case of it doesn't, if f of x is irreducible, then all our fields seem to, like the f to the n,
Yes.
they all should sort of be isomorphic.
Not true. That's close. That's close, but it's not true. For example, if f is the field of rational numbers, here are 2 irreducible polynomials over the rational numbers of the same degree. F of x is x squared plus 1, and f of x or g of x, is x squared minus 2. Right? This one, you know, you get is an I, and this is a square root of 2. Neither of those are rational numbers. So those are irreducible polynomials. If in this case you make the field q of x mod f of x, and here you make the field q of x mod g of x. And both of these things are isomorphic as abelian groups to q plus q, but not as fields. They're both fields, but they're not isomorphic as fields because this field contains the square root of minus 1 in it, and this field contains the square root of 2 in it, but not a square root of minus 1. See, if you want to think of it, this field is a subfield of the real numbers. This one isn't. There's no I in the real numbers. So it can be a different field depending on which polynomial you choose. All right, let's prove this. Yeah, let's take that question which has been waiting for me over here.
I just have a really simple easy question. What's the difference between z mod 3 and z mod 3z? Anything?
None.
Okay.
It's my notation. Sometimes I forget to put the z in.
Okay, so it doesn't mean you're dividing by the ideal rather than by 3z or anything?
It's the same thing. It's the same thing. Yeah. Okay. It's my fault. Let's see why this is true, because Peter was after me on this, and he's absolutely right. This is the way to think of it. You don't have to go through this kind of argument of finding an explicit inverse in each case. Once you know that you have an irreducible polynomial, then the quotient ring is a field. If and only if. Why? Proof. Well, this is going to be cool. We remember that R is a field if and only if it has two ideals. R, 0, and I. And R, I'm sorry. That was our characterization of fields. Now, we remember that the ideals of this ring are precisely the ideals of this ring containing this ideal. Right? So that's if and only if there are exactly two ideals in f of x containing I, which is little f of x, the ideal generated by f of x, namely I and f of x. I mean, those are the only two. If the ideal containing this is itself, then in the quotient ring you get 0, and if the ideal containing it is the whole ring, you get R. Right? All right, let's continue with that. But we know all the ideals of f of x. So this is if and only if f of x is a maximal ideal of the polynomial ring. But, and this is the key but, in this ring, polynomials over a field, we know all ideals in f of x. We determine them, just like we determine all the ideals of the integers. They're the ideals generated by multiples of fixed polynomials. Every I is just multiples of some fixed polynomial by the Euclidean algorithm for polynomials. And remember that this was the polynomial in I which had least degree. Okay. So, we now have to figure out what is the condition on f that it not be contained in any other proper ideal. But I claim that the ideal f of x is contained in the ideal generated by g of x if and only if g of x divides f of x. Right? I mean, this just says that f of x, which is a particular element in this ideal, has to be a multiple of g of x, which is just a divisibility condition. The elements in this ideal are just multiples of g of x. So therefore, we're going to get an ideal containing f of x precisely when we can find a monic polynomial that divides f of x. Now, if f is irreducible, here, The only monic polynomials that divide f of x are f of x and 1. If there were any polynomial of smaller degree that divided it, it wouldn't be irreducible. If this polynomial is f of x, you get this ideal. If this polynomial is 1, you get the whole ring, and you get only those two ideals. Conversely, if this is a field, then any ideal squeezed between here and here has to either be this or that, which says in this case that g of x is equal to f of x. If a monic polynomial of the same degree divides f of x, it has to be equal to f of x. And in this case, if g of x were this, it would say g of x was the monic polynomial 1. And so there were no factors. Okay? So the criterion for this extension process to give you a field is that you have to work with an irreducible polynomial. So we were able to produce a field with 9 elements precisely because we found an irreducible quadratic polynomial. If we wanted to produce, let's work this argument a little harder. So if we were Galois and we had proved that any field had only p to the n elements, and we wanted to produce a field of order p squared, let's call it f prime of order p squared, we need an irreducible quadratic polynomial x squared minus c over the field of p elements. Well, actually, it doesn't have to look like this. It could be, sorry, x squared plus bx plus c over the field of p elements. If we can find such an irreducible quadratic polynomial, then by doing this construction, we would get a field of p squared elements. If there is no such irreducible quadratic polynomial, this construction isn't going to work. Okay, so I'm going to show you how to do that now. That'll be the last thing. So the case p equal 2 is a little weird, because when p is equal to 2, you can't complete the square and use the quadratic formula. You know, the quadratic formula requires that, you know, the roots of this are, you know, minus b plus or minus the square root of b squared minus 4ac over 2a. But this 2 is a nuisance if you're over the field of 2 elements. And that 2 comes from completing the square. So p equal 2 is a special case. Take the polynomial x squared plus x plus 1. I claim this is irreducible. Why? Because it has no roots in Z mod 2Z. The only elements in this ring are 0 and 1. So to see that it has no roots, you have to try 0, and then you have to try 1. If you try 0, you get 0 squared plus 0 plus 1, which is 1. If you try 1, you get 1 plus 1 plus 1, which is 1. So no substitution of an element in the field gives you 0. So polynomial has no roots. Since it has degree 2, if it has no roots, it has no linear factors, therefore it's irreducible. So there you are. There's your field of 4 elements. Field of 4 elements, Z mod 2, x, modulo the ideal generated by x squared plus x plus 1. That's a nice multiplication law to work out as you work out the overflow. Okay? Now, let's assume p is bigger than 2. So we're going to take a look at a polynomial like this. F of x is x squared minus c will be irreducible if c is not a square in Z mod PZ. Right? Because that means there's no roots. That's what we did last time with p equal 3. We took c equal to 2. So if we can find an element in Z mod PZ which is not a square, then we've constructed an irreducible polynomial, and we've got a field of p squared elements. Agreed? So how do we know that there's some element that's not a square? Well, we could try 2. 2 worked for 3, right? Is 2 a square mod 5? No, it isn't, because mod 5, find 1 squared is equal to 1, 2 squared is congruent to minus 1, 3 squared is congruent, well, 2 squared is 4. 3 squared, which is 9, which is also 4. 4 squared is 1. So 2 is not a square. Mod 5. That looks good. So maybe the polynomial x squared minus 2 will always work. However, when we go mod 7, we find but 3 squared is congruent to 2 mod 7. So x squared minus 2 is not irreducible over z mod 7z. And in fact, there's no single polynomial that works. You can't find some integer c which is not a square at all primes p. It's a known fact. So you have to be a little cleverer. And in fact, there are primes p where the first 100 integers c, or the first 1,000 integers c, or the first 1,000,000 integers c are all squares. That's a frightening thought, right? You say, well, 2 doesn't work, 3 will work. Well, you can find a prime where 3 doesn't work. And then you can find a prime where 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 billion don't work. So that's very discouraging. So to prove that there's a field of p-squared elements by this method, I have to abstractly show you that there's something in the field of p elements that isn't a square without actually telling you what it is. Isn't that disappointing? So that when you actually want to compute with the field of p-squared elements, you're going to have to go find one. You're going to have to go find a c. But now I haven't got time to find a c for you, so I'm just going to show you that there is some element which is not a square. So here's the cool argument, again due to Gauss. Actually due to Euler. That some c in z mod pz is not a square. Well, z mod pz star, that's the non-zero elements, is an abelian group of order p minus 1. And we consider the map from this group to itself. Call it a homomorphism. Let's call it H. H of A is equal to A squared. So you take every element and you map it to its square. Now that is a group homomorphism because you're in an abelian group. Group homomorphism because H of AB, which is AB squared, is AB times AB. And since we're in an abelian group, that can be written as A squared times B squared, which is H of A times H of B. It's a group homomorphism. The claim that we can find a non-square is the claim that this homomorphism is not surjective. Right? Because 0 is a square. So if we're going to find a non-square, it should be some non-zero element. And if that element is a square, it has to be the square of some non-zero element. So it should be the image of this homomorphism. All right. So the claim is H is not surjective. So there are non-squares, are C in Z mod PZ star, which are not of the form C is equal to A squared. And taking any such C and taking this polynomial gives you a field of p squared elements. Okay? And it turns out in this case, and it's a weird thing, that all those fields are isomorphic. For finite fields, it turns out they're isomorphic. In this case, they're not. Okay? All right. To prove it's not surjective, I'm going to argue as follows. This group has the same order as this group. The image of a group homomorphism, right, is this group modulo the kernel of the homomorphism. So this map will be surjective if and only if it has no kernel. If and only if the kernel is trivial. Proof: this is equivalent to the statement that the kernel of H is just the element 1. Because you have a map from a group to itself, so it'll be a surjective map if and only if it's a one-to-one map. Because we know that the image is the quotient of this group by the kernel. If there's a non-trivial kernel, the quotient group will have order less than p minus 1. What is the kernel of this map? But, you got it. But the kernel of H consists of the elements A in Z mod PZ star such that A squared is congruent to 1 mod P. And there are exactly two elements in that. Namely, it's the elements plus or minus 1. And they're distinct because I assumed that P was bigger than 2. In the case of squaring on Z mod 2 star, well, Z mod 2 star is a group of order 1, so in that case, this map is an isomorphism. But once P is bigger than 2, there are two elements whose square is 1. The reason there are two elements whose square is 1 is this is equivalent to the fact that A squared minus 1 is divisible by P. And A squared minus 1 factors is A minus 1 times A plus 1. And if a product of two numbers is divisible by P, P has to divide one of them. And that means either A is 1 mod P or minus 1. So since the kernel contains two elements, the image consists of P minus 1 over 2 elements. Image of H of order P minus 1 over 2. So in fact, half of these elements are squares, and half of them are non-squares. We don't know which half. That's the whole theory of quadratic reciprocity that Gauss developed. But there have to be a large number of non-squares. It's possible that the first million terms are all squares, but then there have to be a million somewhere else that are non-squares. And that's a non-constructive proof of the existence of a field of p squared elements. You can imagine how much fun it is to prove that there's a field of p cubed elements, or p to the fourth, because then we have to prove that there's an irreducible polynomial of degree 3, or 4, or 5. So that's a challenge that we'll solve in Math 123. Okay, good luck in the review session. I'll see you Monday for the exam.